The origins of the SR-71 Blackbird trace back to the Cold War's escalating intelligence race between the United States and the Soviet Union. By the late 1950s, the U.S. Air Force and the Central Intelligence Agency recognized that existing reconnaissance platforms, such as the U-2, were becoming increasingly vulnerable to advanced surface-to-air missile systems like the Soviet S-75 Dvina, which had successfully downed Gary Power's U-2 over Sverdlovsk in 1960. The incident underscored the urgent need for an aircraft capable of flying higher, faster, and with greater survivability against emerging air defense threats. Strategic planners required a platform that could penetrate deep into denied airspace, collect high-resolution photographic and electronic intelligence, and exit before interception was possible. Lockheed's Advanced Development Projects Division, better known as the Skunk Works, was tasked with delivering this next-generation reconnaissance aircraft. Under the leadership of Clarence Kelly Johnson, the design team pursued radical solutions. Initial concepts evolved from the A-12 Oxcart, a CIA project emphasizing extreme altitude and Mach 3+ speed. Johnson's team experimented with titanium airframes to endure the aerodynamic heating at such speeds, an approach almost unprecedented in aviation. Titanium was difficult to work with, requiring entirely new fabrication methods and specialized tooling. Complicating matters further, the U.S. sourced much of its titanium ore covertly from the Soviet Union, the very adversary the aircraft was designed to surveil. The design phase pushed the boundaries of aerodynamics and propulsion. The airframe's distinctive Chinese, sharp, extended edges along the fuselage were incorporated to improve stability at high speeds while also contributing to lift. Stealth was a consideration even before the term entered common use. The Blackbird's shape and radar-absorbing materials reduced its cross-section, making it harder to detect. Johnson's team partnered with Pratt & Whitney to create the J-58 turbojet engines capable of sustained operation in afterburner for unprecedented periods, effectively acting as hybrid turbojet ramjets at cruise speed. Each system, avionics, fuel management, cooling, and even the pilot's pressure suit, was custom-built for the extreme operational envelope envisioned. By the early 1960s, wind tunnel testing and small-scale prototypes validated the fundamental aerodynamic principles, but the project's complexity led to numerous engineering challenges. The aircraft's skin had to expand under heat without compromising structural integrity, requiring corrugated titanium panels that appeared unfinished but were essential for thermal expansion. Fuel leakage on the ground was considered normal, as the special JP-7 fuel sealed the tanks only once the airframe heated up during flight. The reconnaissance systems, including high-resolution cameras and side-looking radar, demanded stabilization and vibration damping at speeds exceeding 2,000 miles per hour, a feat never before attempted. The A-12 program's success provided a stepping stone, but the U.S. Air Force required a larger, more versatile platform with improved sensors, defensive countermeasures, and range. This led to the birth of the SR-71 design, a stretched, refined, and mission-optimized evolution of its CIA predecessor. The transition marked not just a shift in specifications, but also in operational doctrine. While the A-12 was a clandestine asset, the SR-71 would be an overt symbol of American technological superiority, intended to operate under military command and support a broader array of intelligence missions worldwide. When the first production SR-71 rolled out in 1964, it embodied nearly every advanced aerospace technology available at the time. It was a product of necessity and innovation, built to survive and excel in the most hostile air defense environments on Earth. The stage was now set for one of the most demanding prototype and testing phases in aviation history. The prototype and testing era of the SR-71 program began with an unprecedented set of challenges. Following the rollout, the aircraft underwent a series of ground tests to validate its systems before attempting high-speed, high-altitude flights. The unique nature of the Blackbird's design meant that virtually no conventional testing procedures applied. From the start, Lockheed and the Air Force faced the reality that many of the aircraft's critical systems could only be proven in flight. The first SR-71 flights were conducted from Groom Lake in Nevada, chosen for its remote location and long runway, essential for an aircraft that required extensive space to accelerate and decelerate. Initial flights quickly revealed both the potential and the complexity of the design. At lower speeds, the SR-71 was not especially agile, and the massive J-58 engines took time to spool up to full power. However, as the speed increased toward Mach 3, the aircraft's aerodynamic efficiency improved dramatically. The Chine configuration, which had been a bold theoretical choice, proved effective in generating lift and stability at extreme speeds. Test pilots also discovered the transition phase where the J-58's operation shifted toward a ramjet-like mode, allowing the engines to maintain thrust efficiently even as conventional turbojets would begin to lose performance. One of the most critical hurdles was the issue of thermal expansion. The titanium airframe expanded several inches in flight, causing significant design adaptations in the joints, panels, and fuel systems. The fuel leaks observed on the ground, initially a source of concern for some engineers, were confirmed to be an intentional byproduct of this thermal expansion. Only after heating during supersonic flight would the airframe seal completely, eliminating leaks and allowing the JP-7 fuel to remain contained under operational conditions. Special fuel additives were also required to withstand the extreme heat, as standard aviation fuels would vaporize or ignite prematurely at Mach 3 temperatures. The flight test program was rigorous and often dangerous. Pilots trained extensively for the physiological demands of sustained high-altitude operations, requiring custom-built full-pressure suits that resembled those used by astronauts. These suits provided both life support in the event of cockpit depressurization and thermal protection against the heat radiating through the cockpit walls at cruising speed. Test flights incrementally pushed the aircraft higher and faster, with engineers closely monitoring telemetry for any sign of structural stress, control surface instability, or engine anomalies. Instrumentation played a critical role in refining the design. Vibration analysis led to adjustments in the camera mounts and sensor packages to ensure image clarity despite the intense aerodynamic forces. Heat-resistant sealants, composite materials, and redesigned engine inlets were tested to optimize performance. The inlets, controlled by an automated system, were critical in managing shockwaves entering the engines at high speed. Early malfunctions in these systems caused surges that could lead to compressor stalls, prompting multiple redesigns before reliable operation was achieved. By the mid-1960s, the test program had validated the SR-71's ability to cruise at sustained speeds above Mach 3 and at altitudes exceeding 80,000 feet. The combination of speed, altitude, and sensor capability meant that no adversary could intercept or track it effectively during a mission. These trials also confirmed the aircraft's resilience. Despite the extreme operational envelope, structural fatigue was minimal, and engine performance remained stable with proper maintenance and calibration. The conclusion of the prototype and testing phase marked the transition of the SR-71 from an experimental platform into an operational asset. It was now ready to enter service, but its integration into active reconnaissance missions would demand new tactics, specialized training, and coordination across multiple branches of the U.S. defense and intelligence community. The stage was set for the Blackbird to take its place as the most advanced reconnaissance aircraft of its time. The SR-71's entry into service in 1966 marked a significant leap forward in aerial reconnaissance capabilities. Assigned to the U.S. Air Force's Strategic Air Command, the aircraft was initially deployed to Beale Air Force Base in California, where specialized facilities and training programs were established to handle its unique operational requirements. From the outset, the Blackbird's missions were planned with precision, involving dedicated ground crews, intelligence analysts, and pilots who underwent rigorous selection and preparation. Flying the SR-71 required not only exceptional piloting skills, but also the ability to manage complex onboard systems while enduring the physical strain of sustained high-altitude, high-speed flight. Early operational missions were designed to test the aircraft's reconnaissance potential in real-world conditions. The SR-71 quickly demonstrated its value by overflying critical hotspots, where conventional reconnaissance methods carried high risk. Its ability to cover vast distances in a fraction of the time previously required allowed the U.S. to gather near real-time intelligence on geopolitical developments. Routes over Southeast Asia, the Middle East, and along the borders of the Soviet Union and China became routine, with the Blackbird often penetrating contested airspace before adversaries could mount an effective response. This speed advantage rendered surface-to-air missiles and interceptor aircraft largely ineffective against it. One of the key strengths of the SR-71 in its early service years was its suite of advanced sensors. High-resolution optical cameras could capture images of targets from altitudes above 80,000 feet, while side-looking radar and infrared systems provided coverage through clouds or in low-light conditions. Electronic intelligence equipment allowed the aircraft to map radar installations and communication nodes, offering a detailed picture of enemy air defense networks. The rapid collection and delivery of this intelligence transformed operational planning, giving military and political leaders unprecedented insight into adversary capabilities and movements. Reactions from pilots and military leadership were overwhelmingly positive, though tempered by the awareness of the aircraft's demanding maintenance and logistical needs. Each SR-71 sortie required extensive pre-flight preparation, including fueling with JP-7, inspection of the airframe for heat-induced wear, and coordination with aerial refueling tankers to extend range. The aircraft's reliance on in-flight refueling made it possible to conduct missions spanning continents without the need for forward basing in potentially vulnerable locations. While the Blackbird never carried offensive weapons, its very presence acted as a strategic deterrent. Foreign militaries quickly learned that the SR-71 could observe sensitive installations with impunity, often prompting them to move assets or alter activities in anticipation of overflights. Soviet MiG-25 interceptors, among the fastest fighters of the era, attempted to engage but could not reach the Blackbird's combination of altitude and speed. Surface-to-air missile launches were frequent during its missions, but none successfully brought down the aircraft. The introduction of the SR-71 also had a profound effect on reconnaissance doctrine. It encouraged the integration of rapid intelligence gathering with immediate analysis, reducing the time between observation and action. In this way, the Blackbird not only provided strategic information but also enhanced tactical decision-making in dynamic situations. By the end of its first full year in service, the aircraft had proven its ability to operate reliably in the most hostile environments and had firmly established its reputation as an unparalleled reconnaissance platform. The early operational success of the SR-71 set the stage for its long-term role in global intelligence gathering. However, as the scope of its missions expanded, the aircraft and its crews would face new challenges, both from evolving enemy defenses and from the demands of adapting the platform to a variety of theaters and geopolitical situations. This would lead to refinements in tactics, technology, and maintenance procedures that would keep the Blackbird relevant for decades. During its prime operational years, the SR-71 became a cornerstone of U.S. strategic reconnaissance, adapting to a wide array of mission profiles and environmental challenges. While its core function remained intelligence gathering, the scope and complexity of its operations evolved significantly in response to shifting geopolitical priorities and the continuous advancement of enemy defenses. Missions were planned with meticulous precision, often involving multiple aerial refuelings, complex routing to avoid predictable patterns, and coordination with satellite surveillance to create a layered intelligence network. One of the aircraft's defining strengths was its ability to conduct deep penetration reconnaissance without the need for armed escorts or suppression of enemy air defenses. This autonomy allowed the SR-71 to operate in highly contested areas, including over regions bristling with surface-to-air missile systems and high-speed interceptors. Despite the numerous attempts by adversaries to track and intercept it, the Blackbird's unmatched combination of Mach 3+ speed and operational ceiling rendered such efforts futile. Records indicate that over the course of thousands of missions, not a single SR-71 was lost to hostile action, a testament to its performance and the discipline of its flight crews. The aircraft's operational flexibility extended to diverse theaters of engagement. Over Vietnam, the SR-71 provided real-time intelligence on troop movements, supply lines, and air defense positions, allowing U.S. forces to plan strikes with greater precision. In the Middle East, it monitored ceasefire agreements and tracked the movement of military equipment across borders during periods of heightened tension. Along the periphery of the Soviet Union, it mapped air defense radars, missile installations, and naval activity, providing critical insight during moments of strategic uncertainty. Success was not without setbacks. The SR-71's complexity made it a high-maintenance platform, and its extreme operating conditions placed constant strain on its engines, airframe, and avionics. Thermal stress was an ever-present concern. Prolonged flights at top speed could cause material fatigue and accelerate wear on critical components. Engine inlet unstarts, sudden disruptions in airflow remained a recurring issue despite technological refinements, requiring pilots to react instantly to stabilize the aircraft. Each mission placed substantial demands on the maintenance crews, who often worked around the clock to ensure readiness for the next sortie. Tactically, the Blackbird's role shifted in response to emerging reconnaissance technologies. While satellites offered broad area surveillance, the SR-71 excelled at rapid response missions where immediate intelligence was required. Its speed allowed it to be tasked and deployed within hours, a capability satellites could not match. In certain cases, it served as a verification tool, confirming or disproving intelligence gathered by other means, such as electronic intercepts or imagery from lower altitude aircraft. The aircraft's adaptability also extended to onboard systems. Sensor packages were upgraded over time to improve resolution, expand electronic intelligence capabilities, and enhance performance in adverse weather conditions. These upgrades ensured that the SR-71 could keep pace with the growing sophistication of enemy countermeasures, maintaining its relevance even as global surveillance technology advanced. Through years of operational deployment, the SR-71's record of success was unparalleled. It consistently delivered high-value intelligence that shaped military strategy and informed political decisions at the highest levels. The absence of combat losses, combined with its extraordinary mission reliability, cemented its reputation not only as a technological triumph but also as an operational asset without equal. Yet, as the Cold War entered new phases and reconnaissance requirements evolved, the Blackbird would undergo significant modifications and adaptations to ensure its continued dominance in the intelligence arena. As the SR-71 matured in service, Lockheed and the U.S. Air Force implemented a series of modifications to extend its operational relevance and adapt it to emerging intelligence needs. The aircraft's base configuration was remarkably advanced for its time, but evolving threats and technological opportunities demanded continual refinement. One of the most significant areas of development was in sensor technology. The original high-resolution optical and infrared imaging systems were supplemented with improved panoramic cameras, enhanced side-looking airborne radar, and upgraded electronic intelligence receivers capable of detecting and classifying a wider range of radar emissions. These improvements allowed the Blackbird to gather more comprehensive intelligence in a single mission, reducing the need for repeat flights over the same area. Engine enhancements were another focus. The Pratt & Whitney J58 power plants received incremental upgrades to improve reliability and efficiency under sustained high-speed operation. Advances in inlet control systems reduced the frequency of unstarts, increasing mission safety and performance. The fuel system also underwent refinements, including better management of the JP-7's temperature and flow, which improved operational stability during extended missions that required multiple aerial refuelings. Variants of the SR-71 emerged to fulfill specific roles. The SR-71B served as a trainer, equipped with dual controls and an elevated rear cockpit for instructor visibility, ensuring that new pilots could gain experience with the aircraft's demanding flight characteristics before undertaking operational missions. The SR-71C, built from a combination of testbed components, functioned primarily as a training and test aircraft. While these variants were not typically used for frontline reconnaissance, they were critical in sustaining the Blackbird program's operational tempo by preparing crews without taking mission-capable aircraft out of service. Upgrades also addressed survivability in the face of improving enemy defenses. Newer generations of surface-to-air missiles posed potential risks, prompting the integration of advanced electronic countermeasures, including radar jamming systems and expendable decoys. The aircraft's radar cross-section was further reduced through refinements in surface coatings and materials, building upon its original stealth-oriented design principles. These measures ensured that even as adversaries improved their detection and tracking systems, the SR-71 maintained its near immunity to interception. Beyond its primary reconnaissance role, the Blackbird contributed to experimental and research programs. In cooperation with NASA, modified SR-71s conducted high-speed aerodynamic and propulsion studies, testing experimental sensors, materials, and even space-related technologies. This collaboration provided valuable data for the development of future high-speed aircraft and spacecraft, reinforcing the SR-71's status as more than just an intelligence asset. It was also a flying laboratory for cutting-edge aerospace research. International deployment was considered but never realized in the form of direct foreign sales. The aircraft's capabilities were deemed too sensitive for export, though Allied nations benefited indirectly from intelligence gathered during joint operations. However, the Blackbird's technological advancements influenced aircraft development worldwide, pushing other nations to explore high-speed reconnaissance concepts, though none achieved a comparable operational platform. By the late stages of its career, the SR-71 had evolved into a highly specialized system, with each airframe incorporating decades of incremental improvements. These modifications ensured that even as satellite reconnaissance became dominant, the Blackbird retained unique capabilities that no other platform could match. The culmination of these technological and operational refinements would shape the aircraft's enduring legacy, influencing both its eventual retirement and its place in the history of aviation innovation. The global impact and legacy of the SR-71 Blackbird extended far beyond its operational service. From the moment it entered active duty, it represented not only a leap in reconnaissance capability, but also a symbol of American technological superiority during the Cold War. Its presence in the strategic arsenal provided a psychological advantage. Adversaries were acutely aware that the United States could observe sensitive sites anywhere on the globe, with little warning and no realistic chance of interception. This persistent capability forced other nations to adapt their military postures, conceal activities more carefully, and invest heavily in air defense systems that still could not reliably challenge the Blackbird. Operationally, the SR-71 proved that manned, high-speed reconnaissance aircraft could coexist with and complement emerging satellite systems. Satellites offered persistent coverage and global reach, but their fixed orbits made them predictable, and they could not be quickly repositioned in response to unfolding events. The SR-71 filled that gap by providing rapid response intelligence collection capable of being tasked and airborne within hours. In situations requiring confirmation of satellite data or immediate assessment of a crisis, the Blackbird's speed and flexibility were unmatched. Its influence on future aircraft design was profound. The aerodynamic principles perfected in the SR-71 program, particularly the use of Chinese for lift and stability at high speeds, found applications in subsequent high-performance aircraft. The extensive use of titanium and heat-resistant composites informed material science for both military and aerospace industries, including spacecraft design. The inlet control systems and propulsion integration developed for the J-58 engines became reference points for later supersonic and hypersonic research. Even stealth technology benefited from lessons learned in reducing the Blackbird's radar cross-section without compromising performance. Culturally, the SR-71 achieved an iconic status rarely attained by military aircraft. Its sleek, futuristic profile and record-breaking performance captured public imagination, while its classified missions and aura of secrecy fueled intrigue. It set multiple world records for speed and altitude, records that still stand, which further cemented its reputation as the fastest air-breathing manned aircraft ever built. For the crews who flew and maintained it, the Blackbird became more than a machine. It was a demanding but trusted partner, capable of extraordinary feats when handled with skill and discipline. The decision to retire the SR-71 in the late 1990s was driven by a combination of factors: the high cost of operation, the increasing capabilities of reconnaissance satellites, and shifting strategic priorities after the Cold War. However, its retirement did not diminish its standing in aviation history. Several aircraft were preserved in museums across the United States, where they continue to draw attention from engineers, historians, and the public. These preserved examples serve as enduring reminders of the extraordinary engineering achievement and operational success the SR-71 represented. In the broader context of military history, the SR-71 stands as a unique achievement. An aircraft that entered service ahead of its time, performed flawlessly under extreme conditions, and left a legacy that influenced multiple generations of aerospace development. Its combination of speed, altitude, and reconnaissance capability remains unmatched, and its legacy endures as a benchmark for what is possible when technological ambition meets strategic necessity. The story of the Blackbird is not just about the fastest spy plane ever built. It is a testament to the power of innovation under pressure and the enduring impact of engineering excellence. Among the lesser-known chapters of the SR-71's history are the specialized missions, experimental programs, and planned developments that never reached full maturity. While its primary role as a high-speed reconnaissance platform was well established, the Blackbird was also used in capacities that pushed the limits of aerospace research and covert operations. Some of these activities were declassified only decades later, while others remain obscured by official secrecy, leaving a fragmented but fascinating record of its broader contributions. One such area was the partnership with NASA, which began in the 1970s and extended into the 1990s. Selected SR-71s were transferred to NASA's Dryden Flight Research Center, where they served as testbeds for high-speed aerodynamics, thermal protection materials, and advanced avionics. These flights produced critical data for programs such as the Space Shuttle and hypersonic vehicle development, examining how heat-resistant materials and airframe designs behaved under sustained high Mach conditions. The aircraft also tested new sensor systems and explored concepts for future high-speed reconnaissance and strike platforms. In the realm of intelligence operations, there are indications that the SR-71 was evaluated for roles beyond strategic reconnaissance. Some missions reportedly involved the deployment or control of unmanned aerial vehicles at extreme altitudes and speeds, using the Blackbird as a mothership for smaller drones intended to penetrate particularly hazardous airspace. Though the concept showed technical promise, operational risks and the complexity of integrating drone release systems into the SR-71's airframe limited its deployment. Certain planned upgrades to the SR-71 never materialized due to budget constraints or shifting priorities. Proposals included fitting the aircraft with more advanced radar systems, integrating near real-time data transmission to ground stations, and even modifying the platform for rapid global strike capability. These ideas reflected the constant search for ways to leverage the Blackbird's speed and reach in new strategic contexts. However, the end of the Cold War and the rising dominance of satellite reconnaissance made it increasingly difficult to justify the expense of such upgrades. The Blackbird also participated in missions designed to test the limits of human endurance in extreme flight environments. Pilots and reconnaissance system officers frequently operated at altitudes above 80,000 feet for hours at a time, requiring specialized life support systems, pressure suits, and cockpit modifications. Data gathered from these missions informed not only military aviation but also spaceflight medicine, contributing to the development of procedures and equipment for astronauts operating in similar physiological conditions. Even in retirement, the SR-71 has remained a point of reference for aerospace innovation. Engineers developing hypersonic aircraft and unmanned reconnaissance platforms still study its propulsion integration, thermal management techniques, and aerodynamic profile. The aircraft's blend of speed, stealth, and endurance continues to influence classified research into next-generation systems intended to operate in environments where conventional aircraft or satellites are vulnerable. In these less publicized roles, the SR-71 proved itself to be far more than a single-purpose intelligence platform. It became a versatile tool for exploration, testing, and boundary pushing in both military and civilian aerospace fields. These unseen chapters add depth to the legacy of the Blackbird, underscoring the reality that its contributions cannot be measured solely by the missions it flew in the open record. Much of what it achieved, and perhaps some of its most significant advances, remain locked away, testament to a machine whose story is still in part untold. The SR-71's later years were marked by a complex interplay of operational excellence, political debate, and shifting strategic priorities. By the late 1980s, the aircraft remained unmatched in its performance, yet its future became increasingly uncertain. The operating costs were substantial. Each hour of flight required many more hours of intensive maintenance, and the specialized support infrastructure, from titanium machining facilities to JP-7 fuel production, demanded a significant budget. At the same time, reconnaissance satellites had matured into highly capable intelligence-gathering assets, providing coverage without risking aircrews or requiring politically sensitive overflights. Despite these trends, senior commanders and intelligence officials continued to advocate for the Blackbird's retention, citing its unique ability to respond rapidly to crises. Satellites could not be tasked on demand for emergent threats, and other aircraft lacked the combination of speed, altitude, and sensor range the SR-71 offered. This capability proved invaluable in late Cold War flashpoints and regional conflicts, where immediate intelligence could influence military and diplomatic decisions within hours. However, these arguments were increasingly countered by those who believed that emerging technologies, such as real-time satellite downlinks and stealthy unmanned systems, would eventually make the SR-71's role redundant. The first formal retirement came in 1990, driven largely by budgetary considerations and confidence in satellite reconnaissance. Yet geopolitical events quickly revealed the gap left by the Blackbird's absence. During the Gulf War, commanders found that the speed and adaptability of the SR-71 would have complemented satellite and UAV coverage, providing faster intelligence updates in a fluid operational environment. This realization, coupled with lobbying from military leaders, led to a brief reactivation of a small SR-71 fleet in the mid-1990s. Upgrades during this period included improved sensor systems, GPS navigation, and limited capability for real-time data transmission to ground stations. However, the aircraft's second life was short-lived. Political disagreements over funding, combined with the ongoing shift towards space-based reconnaissance and advanced UAV programs, resulted in its final retirement in 1998. By that time, the cost of maintaining the unique infrastructure and specialized personnel for a small fleet was seen as unjustifiable, even though no alternative platform could match the SR-71's full performance profile. Post-retirement, many of the surviving aircraft were preserved in museums, including the Smithsonian National Air and Space Museum, where the Blackbird continues to inspire engineers, historians, and aviation enthusiasts. Former pilots and reconnaissance system officers have provided rare insights into the aircraft's operation, but much about its missions remains classified, ensuring that its mystique endures. The SR-71's twilight years illustrate the challenge of balancing technological superiority with economic and strategic realities. While it ended its career without a direct successor capable of replicating its full set of abilities, the aircraft left an operational and technological legacy that continues to shape reconnaissance doctrine. Its departure closed a chapter in which speed and altitude were the ultimate defenses, replaced by an era emphasizing stealth, persistence, and space-based observation. Yet the Blackbird's reputation as the fastest, highest-flying operational aircraft in history remains untouched, ensuring its place in the annals of aviation as a pinnacle of Cold War engineering. The enduring reputation of the SR-71 has been reinforced by the numerous world records it set, many of which remain unbroken decades after its retirement. In July 1976, an SR-71 established the official absolute speed record for a manned, air-breathing aircraft, over 2,193 miles per hour, while also setting the absolute altitude record for horizontal flight at 85,069 feet. These records were not anomalies achieved under stripped-down, one-time test conditions. They reflected the aircraft's normal operational performance. The fact that such speeds and altitudes could be sustained for hours during missions rather than achieved in fleeting bursts highlighted the extraordinary engineering behind the Blackbird. The aircraft's performance records were matched by operational feats. SR-71 crews executed transcontinental and transoceanic flights in times that remain unmatched. On its retirement flight to the Smithsonian National Air and Space Museum in 1990, an SR-71 flew from Los Angeles to Washington, D.C. in just 64 minutes, setting multiple city-to-city speed records along the way. These demonstrations were not only testaments to the aircraft's capability, but also served as symbolic farewells, reinforcing its public image as a technological marvel. Culturally, the Blackbird became more than an intelligence asset. It became an icon of speed, precision, and technological ambition. Its distinctive shape, with the long, needle-like nose, sharply angled chines, and massive engine nacelles, became instantly recognizable to aviation enthusiasts worldwide. It appeared in films, documentaries, and even postage stamps, cementing its status as a symbol of the Cold War era's fusion of engineering prowess and strategic necessity. For many, it represented the pinnacle of manned flight before the focus shifted towards stealth and unmanned systems. In the military aviation community, the SR-71's legacy extended into the realm of training and doctrine. Lessons from its operations influenced the design of later reconnaissance and strike aircraft, particularly in areas of high-speed aerodynamics, thermal management, and systems integration for extreme environments. Its operational model, rapid deployment, deep penetration intelligence gathering, and near immunity to interception remains a reference point for next-generation concepts, including hypersonic reconnaissance platforms currently in development. The mystique of the SR-71 has been amplified by the classified nature of many of its missions. While official records detail its performance and general operational history, the specifics of certain flights remain undisclosed. This has fueled speculation about routes, intelligence gathered, and the geopolitical effects of particular missions. Former crew members, while careful not to violate security restrictions, have occasionally recounted narrow escapes from surface-to-air missile engagements, extreme weather conditions at the edge of the atmosphere, and the demanding teamwork required between pilot and reconnaissance systems officer to keep the aircraft operating at its limits. The SR-71's post-service life has also been marked by its preservation as a historical artifact and research subject. Engineers still study its materials and design features to extract insights relevant to modern aerospace challenges. In this sense, the Blackbird continues to contribute to aviation advancement even in static display. It stands as a bridge between the pioneering supersonic research of the 1950s and the hypersonic ambitions of the 21st century, ensuring that its influence persists long after its final flight. If you'd like, I can now continue with Chestina 10 Munner, which would focus on the SR-71's lasting influence on modern reconnaissance doctrine and how its absence shaped subsequent U.S. intelligence capabilities. This would naturally lead toward a strong concluding section. The SR-71's influence on modern reconnaissance doctrine lies in the way it redefined the balance between speed, survivability, and intelligence delivery. Before its introduction, most high-altitude reconnaissance relied on the assumption that altitude alone could protect aircraft from interception. The Blackbird proved that speed was equally decisive. Its ability to outrun threats fundamentally altered the way military planners approached aerial intelligence. Even after its retirement, the operational principles it embodied continued to shape the design philosophy of future systems, whether manned or unmanned. One of the key doctrinal lessons was the value of rapid response intelligence. The SR-71 could be deployed within hours to observe a crisis zone, gather detailed imagery, and return the data before the situation evolved. This capacity became a benchmark for evaluating reconnaissance assets, influencing the operational requirements for later unmanned aerial vehicles and next-generation surveillance satellites. In modern terms, the Blackbird's responsiveness is still unmatched by orbital systems, which must adhere to fixed orbits, and by most UAVs, which cannot match its speed or altitude. Its absence after 1998 forced the U.S. to rely more heavily on satellites and UAVs, leading to shifts in intelligence-gathering methodology. While satellites provided broader coverage, they could not replicate the SR-71's flexibility, and UAVs, though more persistent, lacked the ability to operate in heavily defended airspace without risk. This gap has spurred research into hypersonic reconnaissance platforms capable of achieving similar speeds, altitudes, and penetration capabilities. Many of these programs remain classified, but publicly disclosed research projects and experimental vehicles show clear conceptual lineage to the Blackbird. Technologically, the SR-71's retirement created a vacuum in sustained Mach 3+ flight operations. The specialized skills and industrial base required to build and maintain such an aircraft faded over time, highlighting the challenge of preserving niche aerospace capabilities. Some analysts have argued that the decision to retire the aircraft without a direct successor was premature, citing the operational utility it could have provided in post-9/11 conflicts or during confrontations with peer adversaries in the 21st century. Others contend that the shift towards stealth and real-time satellite communications was inevitable, and that the Blackbird's unique qualities, while impressive, no longer aligned with the evolving threat environment. Nevertheless, the SR-71 remains a point of reference in debates over the future of reconnaissance. It demonstrated that technological boldness could yield platforms that not only met, but exceeded strategic requirements for decades. It also proved that manned aircraft in certain roles could outperform unmanned or space-based systems in responsiveness and adaptability. These lessons continue to inform the development of cutting-edge aerospace programs, even as their details remain behind layers of classification. In the broader sweep of aviation history, the Blackbird's legacy is not just about speed or altitude, it is about a mindset. It showed that when operational necessity and engineering ambition align, it is possible to create an aircraft that stands unmatched for half a century. Whether or not a true successor will ever be built, the SR-71's influence endures in every discussion of how to observe the world's most dangerous places quickly, decisively, and without being caught. It remains, in every sense, the benchmark for high-speed reconnaissance.